Hello math friends, this is AP Calculus section 3.7 Day 1 notes. Today we are going to talk about differentiating logarithmic functions. So first of all, if we want to differentiate a logarithmic function, we can use the prior knowledge that we have of differentiating exponential functions combined with our new knowledge of implicit differentiation. So we begin by writing the log function in its exponential form. And again, what we're talking about right here, this is back to Algebra 2, just this relationship y equals log base a of x can be written as a to the y power equals x. So then we take that equation, a to the y equals x, and we're going to implicitly differentiate it. So d dx of the left and the right side, or dy dx of the left and the right side. So a to the y, the derivative of that is going to be a to the y times ln a. That was from section 3.5, right? The derivative of an exponential function is the function itself times natural log of the base, right? So derivative of a to the y is a to the y ln a. And then the derivative of x is 1. So we end up with dy dx is equal to 1 divided by a to the y over ln a. Okay, and then in this case, a to the y, remember, was x, so 1 over x times ln a. So this leads us to our two kind of important differentiation equations that we're going to be using in this section. The derivative of some log base a function, so not a natural log, some other log base 10, log base 2, whatever, is 1 over x times natural log of the base. And then if we do have natural log of x, we know that the derivative of that is just 1 over x because the natural log of e is 1, right? So that makes the ln of the base part in the denominator just equal to 1 because natural log of e is 1. So if we want to differentiate the following, these are three very basic examples just so that we can get our feet wet here. So y prime in this case, if we have log base 5 of x, we know is going to be 1 over x times natural log of the base. So in this case, ln 5. And that's it. We're done. In example B, remember when you see log but you don't see a base, the base is 10. So this is going to be y prime is equal to 1 over x natural log 10, because in this case the base of our log is 10. And then in our third example, I wrote the example as log, but the base is e, so keep in mind this is really y equals natural log x, and we know that y prime then is just going to be 1 over x times natural log of the base, but natural log of e is 1. So 1 over x times 1 is just 1 over x. All right, in example A, we have log base 5 of, and then it's x e to the x. So we have a product inside of our log. Okay, so whenever I differentiate logarithmic functions, I always think of whatever's in the parentheses as just the stuff, right? So the logarithmic differentiation part, or the outer function differentiation, is just going to be 1 over the stuff times the natural log, or times the natural log of the base, and then times the derivative of the stuff. So in this case, the stuff is going to be product rule when we do the derivative there. So my f prime of x is going to be 1 over the stuff, so 1 over x e to the x times natural log of the base. But now I have to multiply by the derivative of the stuff, and the derivative of x e to the x is going to require me to use the product rule. First d second, so x, and then derivative of e to the x is e to the x, plus second d first, so e to the x, and then derivative of x is 1. And then I can clean this up a little bit. In my numerator, that product rule, both terms have e to the x. So I could certainly factor out an e to the x, and then I would have x plus 1. And then in my denominator, I have x e to the x times ln 5. And then I could cross out the e to the x term So my final answer here will be f of x equals x plus 1 in my numerator and x ln 5 in my denominator. Okay, let's take a look at example B. Before I begin, I am going to rewrite it as f of x equals natural log of x to the 1/5 power. Okay, so the stuff is the x to the 1/5 power. So when I do my derivative, my f prime of x is going to be equal to, and again, it's natural log, so in this case, it's just 1 over the stuff. So 1 over x to the 1/5 power, but now I have to multiply times the derivative of x to the 1/5 power, which is going to be 1/5 x to the -4/5, because 1/5 minus 1 would be -4/5. And now I can clean this up. So f of x equals, in my numerator, I'm just going to have 1, because 1 times 1. In my denominator, I've got x to the 1/5, which is the 5th root of x. And then I have x to the -4/5 coming downstairs, which is going to be the 5th root of x to the 4th. And then don't forget about this 5 right here from the 1/5. That's just a coefficient in the bottom. But notice that these two together, the 5th root of x times the 5th root of x to the 4th, if I were to multiply those would make the 5th root of x to the 5th, which just makes x, right? So my final answer here is going to be f prime of x is equal to 1 over 5 times x. So that one simplified quite nicely compared to what we started with. And then my final example here, f of x equals ln of sine x. This one's a little bit easier. So f prime of x is going to be 1 over the stuff because it's natural log. So 1 over sine x times the derivative of the inner function. So times the derivative of sine x, which is cosine x. So my f prime of x I could write as cosine x over sine x, but that's actually a function that we are familiar with. Cosine x over sine x is equal to cotangent x. All right, so that gets our feet a little bit wet here when we talk about differentiating log functions where we have chain rule involved, where we have a function inside of our log. So keep in mind, it's always 1 over the stuff. If it's an log, times the natural log of the base, and then times the derivative of the stuff when we're doing chain rule. Okay, so now we're going to pull all of our differentiation rules together, including our new rules for logarithms. So we're going to differentiate the following, and then after we're done, we're going to name all the differentiation rules that we used. Okay, so in letter A here, we have the natural log of, and then x plus the square root of x squared minus 1. Okay, so f prime of x, again, my outer function's the natural log. So natural log's derivative is just 1 over the stuff. So it's going to be 1 over everything that's in that parentheses. So x plus the square root of x squared minus 1. Okay. But then I have to multiply by the derivative of what's inside those parentheses. And the derivative of x is 1 plus x squared minus 1 has a square root over it. So that whole thing, x squared minus 1, is to the 1/2 power. So that's going to be 1/2. And then I have the x squared minus 1. And now it's to the -1/2 power. But then I still have chain rule because inside that square root, I still had the x squared minus 1. So now I have to multiply by the derivative of that, which is 2x. So that one had chain rule within chain rule. So that one was pretty complicated. And now let's clean this up a little bit. Let's try to make this look a little bit prettier here. So we have f prime of x is equal to, here I have 1 over x plus the square root of x squared minus 1 times, and then here I have 1 plus, and this would be 1 over 2 times the square root of x squared minus 1 down in the bottom times the 2x, which puts the 2x on top. I can cross out those 2's, so then I have 1 plus x over the square root of x squared minus 1. I can rewrite this. My first term I'm going to keep the same as x plus the square root of x squared minus 1. And then in my second fraction, if I make a common denominator here, so if I make my common denominator x squared minus 1 under the square root, then I have to multiply the 1 by that. So then I would have the square root of x squared minus 1 plus x. And the only reason that this appeals to me is because if you now look at this term right here, which is upstairs, the square root of x squared minus 1 plus x, that's a family. And you look over here downstairs, x plus the square root of x squared minus 1, they are the same. So I can reduce those. So then my final answer, which looks a lot neater, is f prime of x is equal to 1 over the square root of x squared minus 1. But that was some kind of fancy algebra going on there. All right, so which differentiation rules did we use? Well, the first rule that we used was the derivative of a natural log. And then we used the chain rule, and we actually used that twice. Okay. And then obviously the rest of it was just algebraic simplification, which sometimes is easy to get lost in, so we always have to be careful with that. All right, letter B. This one is simpler. We have a product to begin with. We have f of x is equal to sine x times natural log of 5x. So obviously we have to begin with the product rule. So our first function is sine x, and our second function is ln x. So we're going to do first d second plus second d first. So f prime of x is going to be equal to first, which is sine x. Derivative of the second, derivative of ln of 5x is going to be 1 over 5x times the derivative of 5x, which is 5. So that's first d second, plus second d first is going to be ln of 5x, and then the derivative of sine x is cosine x. So now let's simplify. F prime of x is equal to, in the first term, we have sine x times 1 times 5, so that's 5 sine x over 5x. So basically this 5 and this 5 are going to cancel, and we end up with sine x over x for our first term, plus, we can't really simplify anything in our second term, so this is just going to be ln 5x times cosine x. And that is our derivative. So now which differentiation rules did we use? Well, we use the product rule. In the first term, when we did the product rule, the natural log function required us to use the chain rule. We also used a trig derivative when we differentiated sine, and we used the derivative of a natural log. So we used 4 different differentiation rules in one example. All right, letter C, looks like we have another product. So we're going to start with the product rule. X is our first function, and natural log of 1 plus e to the x is going to be our second function. So we're going to begin again with product rule. So f prime of x is going to be equal to first times the derivative of the second. So the derivative of a natural log function is 1 over the stuff. So 1 over 1 plus e to the x times the derivative of the stuff. We've got chain rule, right? So the derivative of 1 plus e to the x is just going to be e to the x. So that's first d second, plus second, so ln of 1 plus e to the x d first, and the derivative of x is just 1. So now we can do some simplifying. Our f prime of x across the top, x times 1 times e to the x, is going to be x e to the x over 1 plus e to the x plus natural log of 1 plus e to the x. And that one is done. And which rules did we use to differentiate that? Well, we started with the product rule. And then we did the derivative of a natural log, and we used the chain rule. All right, letter D is once again another product. So 2x will be our first function, and log of the square root of x will be our second function. So our f prime of x, again, beginning with the product rule, first d second, so 2x, derivative of log of the square root of x is going to be 1 over the stuff, so 1 over the square root of x. Now this time we don't have a natural log, so we have to multiply by ln of the base, so ln 10. And then we have to multiply by the derivative of what's inside the log, the derivative of the stuff, and the derivative of the square root of x is 1/2 x to the negative 1/2 power. That's first d second, plus now we have second, which is log of the square root of x, d first, derivative of 2x is 2. All right, now we have some cleanup to do. So f prime of x is going to be equal to, let's see here, across the top, we've got 2x times 1, so we're going to have 2x. And then in the denominator, we're going to have, let's see, the square root of x and the natural log of 10. And we're going to have, from the derivative of the square root of x, we're going to have the 2 from the 1/2 in the bottom. And then x to the negative 1/2, when we bring it downstairs, is going to become the square root of x in the denominator, which again, we're going to be able to clean this up a little bit over here. So I'm going to put the 2 in the front. So we're going to have 2 times log of the square root of x. Okay. So in the first term, we're going to cross out the 2's, right? And then the square root of x times the square root of x is just going to make x. So actually, this x, this square root of x, and this square root of x are all going to cancel each other out, because square root of x times square root of x is x, and x over x cancels. So I end up with f prime of x is equal to 1 over ln 10 for my first term, plus, now over here, I'm going to do a little fancy algebra footwork. We've got 2 log, and I'm going to rewrite the square root of x as x to the 1/2 power. Well, you know that you can bring an exponent down in front of a log, right? If it's on the whatever's inside the log, that exponent can come in front and become a coefficient. Well, what happens when we bring that down in front? Half of 2 is 1. So basically, the 1/2 and the 2 cancel each other out. So we end up with f prime of x is 1 over natural log 10 plus log x. And that is as simple as we can get. What did we use here? We used the product rule. We used the derivative of an log log. And we used the chain rule. And then after that, we used a lot of algebra. The last part of the notes today is not an example, but is instead just an explanation of what happens when you have an absolute value function inside of a log in terms of differentiation. So we know that absolute value functions look like they are mirrored over their axis of symmetry, right? Absolute value functions make a V shape. We know that the slopes of the left side and the right side are always opposites of each other. And we also know that we've always had to look at left-hand limits and right-hand limits in terms of derivatives when we're talking about absolute value functions. Okay, and log functions with absolute values are no exception. So we have to consider the differentiation of the left side separate from the right side. So if our function is f of x equals natural log of x, then we know that f of x would be natural log of the absolute value of x. Then f of x would be equal to natural log of x on the right side, so if x is greater than 0, and it would be equivalent to natural log of negative x on the left-hand side, or if x is less than 0, right? But if we differentiate both of these functions, on the right-hand side, derivative of ln of x is 1 over x, right? And on the left-hand side, the derivative of ln of negative x is 1 over negative x times the derivative of negative x, which is negative 1. That requires chain rule. But notice that the negative from the chain rule cancels out the negative x in the bottom, or the negative from the negative x in the bottom, and so we still end up with 1 over x. So because of the chain rule, it turns out that the derivative is the same for both the left-hand side and the right-hand sides of the natural log of x function, and the derivative of the natural log of the absolute value of x is 1 over x on the left-hand side and on the right-hand side. So basically what we've learned here is that if you have absolute value around the x inside of your log, it doesn't affect your derivative. You still have the derivative of natural log of the absolute value of x as just 1 over x, and you don't have to worry about left hand and right hand, and that is because of the chain rule.